Okay, hello. This is the theory for chapter 7, which is chapter 7 is work and energy. So, I'd imagine the midterm cutoff has already happened in your course cuz that's like half the course was I mean this is the exact half chapter 7 out of 14, but it delves into like a new topic, right? Anyways, let's start with some definitions. So, work is something that describes the a scenario where a particle is experiencing a force and that makes it go a certain displacement in the direction of the force. So, if we have our box and I'm pushing it this way and it moves this way, there's work being done here. This system has work, right? So work is a description of a scenario where a particle undergoes a displacement due to a force. And it doesn't always have to directly cause the displacement. Like the force doesn't always have to directly cause it for there to be work, right? So in this course we have U is equal to work. That's our variable, right? And there's like the physics, not the physics, sorry, the calculus meaning here, where we take a infinitesimally small amount of work, and the formula for it is F ds cosine theta. I need this. Theta. That's not how you spell theta. There we go. F ds cosine theta, where ds is just distance, but infinitesimal distance. And this angle theta is between the path and the force. So let's say we have it like this, and we have our force going this way. This is where you would get your theta, between the ground and the force, right? Or whatever. The path, which is this way, and the force, which is over here. So that's how you get theta for that term. Anyways, so if you have all these terms, right, and then you integrate, you get U is equal to Fs cos theta, and that is the work. That is the work equation. As you can see, if we go here, in this section of kinetic energy, we go to work, constant force, and it's right here. Is this equation. And you can also see right here, variable force is what we just showed above, right? So, after this, we need to know one thing is that du is a scalar, and when you have a scalar, that means you can take the dot product of two vectors, and that gives you a scalar. So what dot product can we use? Well, we know that force is a vector, but what happens when we dot it with something, right? Well, let's just draw out a scenario here. We have our box. We have our force vector. We have... Now, let's imagine it is here at point 1 and then dotted box here at point 2. Force is constant in this situation, right? So from some arbitrary origin, we have R and R2, right? Now, what we can do is for the total R vector, which would be like here, so for R itself, in terms of vector, we can take it as infinitesimal steps. That was a horrendous misspeak. Infinitesimal steps, right? And this is a vector because these r's are vectors and the forces are vectors. So F dot dr, where these two terms are vectors, will give us a scalar energy du. And not energy, this is work. Yeah. Anyways, that is when it's a scalar. Now, looking back at this cosine equation, what do we know about cosine? Well, between 0 and 90, cosine is positive. At 90, it is 0. So when your angle, when your work, when your force is straight up and your path is straight right, so like this, if this is your force and this is your path, P for path, F for force, well, the force is not going to be moving the particle onto the path because there's no component that even inches it along this way. So it's going to have no work done. So that's how you can imagine that. Anyways, as I was saying, so if we have theta, theta is between 0 and, that's not how you write these, 0 and 90, like this, you get positive work. So positive work. If it is between 90 and 180, you get negative work, right? And then that's same rules apply for like the below the x-axis angles, but that's okay. Yeah. So this is a constant force work. So constant force work, right? And this is vector force work, right? So now we need to look at when we have variable force. And it's going to be the same thing where we're going to have, we're going to take this formula, F dot dr. We're going to change dot dr into, because we know a property of dot products is that it's equal to magnitude of A, magnitude of B, cosine theta. And the magnitude of dr is just ds. Basically, it's this one again. We're bringing this formula back, like so. But now f is a variable. So to fully rewrite this, we're going to have that u is equal to f cosine theta ds. And we're going to put an integral here like this. And this is from point 1 to point 2. This is not like the number 1 to the number 2. This is point 1 to point 2. So you could write this as like S1 and S2. And then u, the work here specifically, is the work done by the force at point 1, or between point 1 and point 2. So the way you'd write it out is like u1 to 2. And this subscript is very important because it helps you keep track of where you're taking your work. So if you have like a question with multiple stages and you just keep writing u everywhere, right? Eventually you're going to be like, which one is for which stage? But if you put your subscript, it'll be very easy to keep that in mind, right? So I still don't have I've got to get an integral hotkey, but that's fine. This is an integral. Let me just integral. So there are, of course, diagrams for this, right? So we have, oh, that's not a straight line. We have like this. So we can represent it with a f cosine theta versus displacement. right? And this is for variable force, by the way, not constant force. Well, it can be constant force, I guess, because you're just going to have, like, let's say we have this curve. The area from point 1 to point 2, so here, is just going to be this integral right here. So the area is just this integral, which means that the area under an f cos theta s graph is work. So keep that in mind, because you could get a question like this, potentially. So, yeah, pretty easy. So, yeah. Also, if you have, like, variable force, that means you have a variable theta, because, like, say the force is, like, or not always, you can have constant theta, but you can have, like, the force is like this at one time, and then it goes up to here like this at another time, right? Which means your theta goes from this to this, if that makes sense. Well, it does. I don't know why. Anyways, yeah. Like, this is S1 and S2 down here. I wrote the points there. So, yeah. Area under this graph gives you this integral, which gives you work from points 1 to 2. Okay. So, now there are some special cases for work. Okay? So, we already went over constant force, which is this stuff here. And we went over the variable force, which is this stuff here. So now we're going to look at work done by weight. Right? And what does work done by weight look like? Well, we have this integral. And we have f, or sorry, not this integral. We have this integral here. Right? Which means we're going to be splitting our these two f and d are vectors, so let's split them into vectors. So for f, we're going to have, and this is work done by weight, so if we imagine weight, right, this is what weight looks like, mg. So it's purely, and we're going to take a 2D approach here, because writing out 3D is not going to change anything, right? This is our positive I and j. So we're going to have 0i minus mgj plus 0i minus mgj dot, and let me actually make this into a vector, dot, we have dxi dyj, or I guess it's plus, not plus dyj, like this, and we're dotting these together, right? So that results in du equal to negative mg dy, right? Which means it's equal to negative mg delta y, because it's the change. And this is for u, so when you integrate both sides, you get u is equal to this, mg delta y. And this is when the whatchamacallit, this is when, this is from y1 to y2, so this is again u1 to u2, right? Now, you might be wondering, there's a negative sign here. Is this ever going to be a positive work? And the answer is yes, there can be positive work. Let's imagine you have this particle here. You want to find the work it takes to get from here, y equals 5, to here, which is y equals 2. Well, if you do delta y, which is y2 minus y1, so 2 minus 5, negative 3, double negative. So when your object or your particle is falling or just moving downwards, moving in the negative direction, that is when your work due to weight will be positive. All right, so yeah, we have now work done by a spring. So this is another special case, work done by spring. Right? So recall we have that Fs is equal to negative Ks, right? So if you think about it, negative is just cosine 180, right? K is a constant and S can be represented as delta S, where it's just compression. So Fs is going to be in the opposite direction of like the movement, because it's representing the compression. So if I draw out a spring, this is a spring, by the way. There, that's more spring looking. Fs acts this way, like that. All right, and as you can see, since it's acting this way, the angle and the path is this way. The angle from this force to this path, I'll draw it up here for more clarity. That's 180 degrees, which is where the negative in Ks comes from, right? So, and we have delta S. So like the second thing is here. So we have S1 is here and S2 is here. So this is S1 and S2 is here, right? So that is fairly nice and easy. So again, we're going to be doing this integral here, but we already have cosine theta as constant, as negative. So it's just going to be that du is equal to Fs ds. And then integrate both sides, we get u. And remember, this is from point 1 to 2, or point A to B, whatever it is in the question, whatever you want to use. You can use point A to B if you like doing it like that. But this is work from 1 to 2. So we have negative Ks ds, and if we integrate negative Ks ds, it's just going to be negative K s squared over 2. From, and this is a delta S squared over 2. So, we can actually eliminate the sign convention here, right? So we know that delta S squared, so delta S squared is equal to, so I'm going to call it SF for S final squared minus S initial squared, right? Now, if we make it negative, which eliminates the sign, we get that it's just equal to SI squared minus SF squared. So if you want to do that, you can do that, right? Does not matter. You just need to make sure to do, like if you were to look at this graphically of a spring force versus S graph, right? Spring force, Fs versus S. You have this, here's your area. If you, this area is positive because it's SF minus SI. So you'd either have to manually put in a negative sign or do S1 minus S2. And this is like squared, right? So either put in a negative sign manually when looking at it graphically, or just flip the order of your subtraction. Both work because that's how subtraction works. It's very nice. Anyways, so if we are compressing a spring, because this was imagining that the block went away from the spring. Let's say this plate is the spring. We're assuming that we moved away from it. Now, what if the spring is compressing alongside what is alongside the spring itself? So let's say the block is attached to the spring and it just keeps compressing. What's going to happen here? Well, in this equation, we would have had negative work, right? Because SF was more to the right, and we're taking this to be positive. So like SF was here, and SI was here. So we would have had negative work. So that doesn't change though, because if we take our spring, and let's say we start here with our block, and it's attached to a spring, and then we go here, right? This is negative work. We already know that. And then if we compress all the way over here, so we compress all the way over here, we're going to get still negative work because of the negative sign in front of the K. That is it. We're always going to have negative work. Unless unless it's specific in the question, but that's okay. Anyways, that is everything for work, right? Now it's time for energy. Now, work is like a thing of energy. Yeah. It's interesting how they wrote that out. Anyways, as I was saying, work is related to energy, right? So let's begin. We're going to have a path and a particle. So let me just write here quickly, energy. Anyways, we're going to have a path and a particle. We're going to have a force that acts this way, whatever it is. And we're going to have the normal and tangential coordinates. So this is tangential and this is normal. Normal and tangential. At this point, we're going to assume we're taking infinitesimally small distances, or displacements, I should say, of ds. And yeah, we're going to have like a 0.1 and a 0.2. That's our diagram. So we know that in the tangential, right, the sum of the forces in the tangential direction are equal to MAT. And since we know that, we can also rewrite this. Oh yeah. And kinematics wise, we know that AT ds is equal to VdV. So we can rewrite this equation as Ft is equal to mv ds dv, or I'm going to call it s prime. S prime. mvs prime, right? And then we split up where our ds is. So we're going to get Ft ds is equal to mv dv, like that. And then integrate both sides from, in this place we're going to go from 0.1 to 0.2, and then for the velocity's sake we're going from velocity 1 to velocity 2. So we're going to get that Ft delta s is equal to m delta v squared over 2 delta v squared over 2, like so. And well, what do we know about this? Half mv squared. This is our kinetic energy, which you should recognize from like old physics stuff. This is kinetic energy, half mv squared. You can get rid of the delta and write it out as half mv2 squared minus half mv1 squared. And that would be kinetic energy 2 minus kinetic energy 1. So what is this telling us? Well, it's telling us that the sum of work, so all work, is equal to delta T. And T here is kinetic energy. T equals kinetic energy, right? This is what it is telling us. U is equal to delta T. And if we look at this, well, that is true. If we were to take T1 to this side, it would be U is equal to T2 minus T1. This is the principle of work and energy. That is how you can relate the two things. Very important principle. A lot of questions are going to use this. So it's important to know that. Yeah. So this equation, which I will rewrite as T2 minus T1, just to respect this here. Remember, because F delta S is work. We know that already. And in the tangential direction. So, this equation is telling us that work causes kinetic energy change. Oops. And if you think about it, right? Um, if I have my box like this, and I apply a force to it, and it moves this distance s, right? If you think about it, it went from rest to moving when work was done, which, yeah, that means there was a change in kinetic energy. And obviously, this is a really simple example, but it gets the point across, so that's fine. Both of these are in joules, by the way. Energy and work, everything is in joules. Joules are the unit. If you want to like derive the derive the unit, you would go joules is Newton meters, and then you would split meters into kilogram meters per second squared, and then it would be kilogram meter squared second squared is a joule. There you go. Nice and easy, right? Work can be positive or negative, right? But energy is only positive. Energy is only positive. Like, let's think about it here. mv squared over 2. Mass is constantly positive, right? Your velocity gets squared, so even if it was negative, it becomes a positive term. And 2 is a constant, which is always positive. So energy is always positive. So work is a description of change, and energy is a description of the state. So, yeah, that's pretty much it. That is the, and let me write that down, principle of work and energy. Now, the reason it's written in this form on the formula sheet is because this is trying to add like intuition to the formula to where you have your initial kinetic energy and you add your work to get your final kinetic energy, right? This is basically saying add the difference of energy to get your final energy. Or if you're looking for like T1, remove the difference in energy, right? So that's what that is. Now, we need to also, one last part of this chapter is power and efficiency. Power and efficiency. Now, efficiency, you're going into engineering, which means you need to think about the efficiency of the things you make. If something isn't efficient, well, what are you using it for, you know? So, but let's think about power. Power, which we denote as P, is the rate of work in a certain amount of time. And what does that mean? What's a rate? Well, it's a derivative. So this is U prime with respect to T, right? du dt. So we know that du is this. And we're going to use the dot product definition here just for simplicity's sake. So that gives us that P is equal to F dot dr over dt. Now, what is dr dt? Well, dr is the path, right? So dr dt is just velocity. So this is equal to F dot velocity. And the unit for power is watts. Watts are just joules per second. That's what a watt is. Very, very useful. Okay. Now, efficiency. Efficiency is the ratio of useful output to the input. So, and we use a little e for this, which is like epsilon. Epsilon. This one. We have epsilon is equal to output over input. And output specifically is useful output. So the output that can actually be used. If you can't use it, there's no point to it. So this value is always less than 1. it can be 0 because you have no output, but it's never equal to 1. And why is that? Well, this is just like a fundamental, I think it's a law of thermodynamics where nothing is ever 100% efficient, something like that. So if nothing is ever 100% efficient, your efficiency is never going to be 1, because this is like you convert it to percentage, like times 100 to convert to percentage. So there's always loss in heat or whatever. Like if we have this system here, what's the efficiency of the system? Well, we applied a force and it traveled a distance, so we get our work. We had T1 is 0 from rest. T2 is whatever velocity was moving at this snapshot instant, right? We inputted this much work and we got the kinetic energy or whatever. We got our output, which was the resultant motion from our input work here, or from our input force here. And it's not 100% efficient because some of the energy gets eaten up by things like friction. There's an opposing friction. It can be lost to heat, right? Like it transforms into heat and loses itself, leaves the system, right? There are many ways to lose power. And those ways, like this efficiency is like a power thing, like input power, output power. But yeah, there's lots of ways to lose power to the environment that you won't always be able to optimize. But that's like not something you worry about, like optimizing it. That's like what you do for your job, whatever. Anyways, that is all the theory for this whatchamacallit, for this chapter. It's actually like more theory than the past few chapters. There have been a little bit of short theory videos, but that's fine. That was chapter 7, work and energy. I really like this chapter, and you can actually, if you wanted to, if you had enough information, that is, you could go back to our old questions, kinetics questions, and you could solve them again with energy and using the principle of work and energy instead of kinematics and force analysis, right? They will give you the same answers. If they don't, then the question was made badly. But yeah, that is chapter 7. Thank you for watching. I hope you learned something. Goodbye.